right, we're going to take a look at section 4.2, prime and composite numbers. So, because it's important to know the difference, especially what a prime number is. So let's take a look. Let's start with the definition of prime. And this is a number, which is a positive integer. So think the natural numbers. Okay, this is the natural numbers. One, two, well, not one, but positive integers starting with 1, 2, 3, with exactly two unique factors. With that, two unique, in other words, different factors. Primarily the number 1 and itself. So if I start thinking about the natural numbers or positive integers, if I look at the natural numbers, we know that we have 1, 2, 3, 4, 5, and I can keep going forever, but I'm going to just sort of go up to the first 12. And if I ask myself, I need two unique factors, 1 and itself. So if I look at that definition, is 1 a prime number? Well, the answer is no, because the only factors that go into 1 are 1 times 1. So 1 is not prime. 1 is called the identity, and 1 is just simply 1. Now, if we think of the number 2, what goes into, what divides 2? Well, the factors of 2 are 1 and 2. Therefore, the only numbers that go into 2 are the numbers 1 and 2. Think of the numbers that go into the number 3. The only thing that divides into the number 3 is 1 times 3, so that's also prime. Now think about 4. 4 is 1 times 4, but it is also 2 times 2. So by definition, it is not prime. 5, the only things going to 5 are 1 and 5. 6, well, 1 goes into 6, 2 goes into 6, 3 goes into 6, so it's not prime. 7, only 1 times 7. 8, well, actually, every even number after the number 2, we know 2 will go into. So all these even numbers will not work because we know 2 automatically divides into them. Well, the definition of prime is 1 in itself. Well, 3 goes into 9, that doesn't work. 1 times 11. So that's how we can figure out some primes. Okay, is just looking at what divides into it. Now we also need to take a look at what are called composite numbers. And again, mathematicians are pretty simple. If we're talking about prime or composite, so the definition of a composite number, a number which is not prime. So if it has anything other than 1 in itself, if it has 3 factors, 4 factors, 5, 6 numbers that will go into it, it's considered composite. So for example, looking on this list up here, 4 was composite because that's 1 times 2. All 3 of those numbers, 1, 2, and 4, will go into it. 6, because the numbers 1, 2, 3, and 6 will divide into 6. Okay, similarly, the factors of 8. So if I list these as factors, 8, what goes into 8? 1 goes into 8, 2 goes into 8, 4 goes into 8, 8 goes into 8. So you've got the idea. So anything that's not prime is considered composite. And in order to look at, and you may remember from school, we used to do something called prime factorization. So let's look at some prime factorization. I think I'm actually going to erase this to leave a little more room. So pause if you need to. And you may remember this from grammar, elementary school. We used to do a couple of things here when we would factor things out. So let's take a look at some prime factorization. And remember, factors are the components of multiplication. So in this case, we've got, all right, so we have a few things. We could do one method, okay, prime factorization methods or models. The first one is what we call factor trees. And you may remember doing this in elementary school. So if I take, for example, the number 1,800, and I go through my rules of divisibility, I could start with 2, but we might be here a while. 2 times 900, 2 times 450, 2 times 225. Or you might go, oh, look, this is 18 times 100. And you ask yourself, is 18 prime? Well, no, because I could make this 9 times 2. Well, is 9 prime? No. Is 2 prime? Yes. So in elementary school, oftentimes we would circle it if it was prime and we knew that branch was finished. But 9 is 3 times 3. And since both of those numbers are prime, the only thing that will go into them is 1 in itself. I'm going to circle it. And then there's several ways to do 100. 10 times 10, 2 times 50, 5 times 20. I'm going to choose for space 4 times 25, and I can factor the 4 and I can factor the 25 into only prime numbers. But no matter what path you choose for factors, when you get done at the end of each branch, you're going to end up with the same numbers that are circled, just maybe not in the same order. And then the proper way to write this out is to say 1,800. And then look at the product of all these, right? This is factorization. So start with the smallest factor, which was 2. And I have 1, 2, 3 of them. So instead of writing 2 times 2 times 2, we'll go 2 to the third. We have 2 3s, so I'm going to say 3 squared. And we have a pair of 5s, so that's 5 squared. And it's common to start with the smallest and increase by the factors. Okay. So some students like factor trees. But if they started with the number 2, it's going to be lopsided. And so we encourage them to start more, try to find things that are larger than 2 or 4. Another way to do this, though, is pretty interesting, and it's called stairs. These are factor stairs. And when I introduce it this way, some students really like it because it's similar to division. So I can start with, I'm going to start with 1,800. And I'm going to start with the smallest prime number that will divide into that. Well, based on the last section, we know 2 will divide into this because it ends in an even number. And 2 goes into this 900 times. And then I'm going to keep dividing by 2 until it won't work anymore. Here, I'm going to put this out here. Since 900 is even, 2 will divide into that 450. Well, 450 is even, so 2 will divide into that 225 times. Well, now 2 won't work anymore because 225 is not even. So then I go to the rule for 3, and 3 says add the digits. 2 plus 2 plus 5 is 9. Since 3 will go into 9, 3 will divide into this. Okay. 3 will go in 75 times. Same rule of thumb, 7 plus 5 is 12. 3 will divide into 12, so 3 will divide into 75. But now 3 will not go into 25, so I move to my next largest prime, which is the number 5. And 5 goes into 25 5 times. And you'll notice this is now written in order. 2 times 2 times 2 to the third. Then it already gives me the 3's in order. And it finishes with that pair of 5's. So it's already written in order as you go up the stairs. And it looks a lot like division. A third way to do this is by how we started, by dividing, by divides, by definition. By definition of divides. So what do I mean by that? Well, I'm going to start with, let me just make a list here. 1800. And think of it as that long division symbol. 2, so here are your divisors. 2 divides 1800 900 times. Then 2 divides 900 450 times. Then 2 divides 450 225 times. And then the same idea, we can go to our next 3 divides into this because these digits add up to 9. And 3 divides into this 75 times. 3 divides into 75 25 times. 5 divides into 25 5 times. And 5 divides into 5 1 time. And so once again, the divisors are all listed. And so I can say 1800 is the same as 2 to the third times 3 squared times 5 squared. So they're just different ways to model. Okay. And then the last I want to talk about is how to figure out how many factors will go into any given number. So if I wanted to make factor trees and I wanted to figure out how many numbers will divide into it, we can of course list them, and I'll give you an example. But there is a theorem I'm going to write down, and then we're going to practice it a few times. Okay, so here's a theorem or a law. So if P and Q are different prime numbers, and N and M are whole numbers, 0, 1, 2, 3, etc. Then P to the N power times Q to the M power has N plus 1 times M plus 1 whole number divisors. And we're going to practice this because this can be very confusing if you try to read it and figure out what it's saying. So let's take a look at this, okay? let's say, for example, I ask you to create a factor tree for the number 24. And we want prime factors that go into 24. So if we do 24, 24 is 8 times 3. Well, 3 is prime, so we're done. 8 is 4 times 2, that's prime. And 4 is 2 times 2. So we are left with 24 is the same as 2 to the third times 3, or times 3 to the first. Okay. So by this theorem, if I have p to the n and q to the m, these are two different prime numbers. Look at their exponents. I have an exponent of 3 and I have an exponent of 1. So this means then that 24 has, and I'm just going to do this, I'm going to color code it. I'm going to go back and rewrite 24 as 2 to the third. I'm going to put that in purple. And 3 to the first, because there's only one of them. So now, according to this theorem, once it's factored out, 2 to the third, 3 to the first, it has, and take a look, n and m come right off of those powers. So this is going to have 3 plus 1 times 1 plus 1. I just took those exponents and put them right in there. Whole number divisors. So 24 has 4 times 2 divisors. So 24 has 8 numbers that will divide into it. All right, let's list them all. List the divisors of 24. So I'm going to do this by pairs. Okay, well, the smallest number that'll go into 24 is 1. So 1 and 24, 1 times 24 is 24. 2 times 12 is 24. 3 times 8. 4 times 6. 5 doesn't work. 6 times 4, I already have it. 8. So I have 1, 2, 3, 4, 5, 6, 7, 8. So divisors of 24 would be this set of numbers. If I listed them in numerical order, 1 goes into it, 2, 3, 4, 6, 8, 12, and 24. And you'll notice the cardinality of that set, 1, 2, 3, 4, 5, 6, 7, 8, is exactly what we said by looking at those powers. Okay. So we're going to do it again. All right. I would like to know, I'm going to do it again. I'll just use this side over here. Let's see. How many divisors does the number 300 have? How many numbers, in other words, how many divisors does the number 300 have? In other words, if you want to write it down, how many numbers go into 300 evenly? Positive numbers go into 300 evenly. Well, you could start listing them, but we could also first determine how many we're supposed to have. So I'm going to first factor 300. I'm going to use a stair method this time. Okay. So I'm going to start with the number 300. I don't know how much room to use. And I'm going to start, well, the smallest prime is the number 2. 2 goes into this 150 times. Well, 2 will go into that 75 times. Well, 75 is 3 times 25. 25 is 5 times 5. So it looks like 300 is the same as 2 to the second times 3 to the first times 5 squared. Now, if I use this theorem, and I now have it in factored form, all I've got to do is look at the exponents and substitute them into this equation. So I'm going to say, well, the number of factors, or I'm sorry, number of divisors. This time, since I have 3 prime bases, I'm going to have 3 of these. And I'm going to have 2 for the first exponent plus 1, 1 for the second exponent, and 2 for that third exponent. So it's going to have 3 times 2 times 4 . Oh, whoops, 2 plus 1. Sorry about that. Somebody else probably caught that already. I just now caught up to you. So I'm going to have 3 times 2, which is 6, and I'm going to have 18 divisors. Now, just to speed up this process for you, if I asked you to list the divisors of the number 300, I'm going to do this in pairs. So let's see, we do have 1 times 300, 2 times 150, 3 goes into 300 100 times. And notice as this left column is getting larger, this right column is getting smaller. Well, 4 will go into this 75 times. 5 times 60 gives me 300, which means 6 times 50 gives me 300. The rule for 7 doesn't work. The rule for 8 doesn't work. The rule for 9 doesn't work. But 10 goes into 330 times. So notice these numbers are getting closer together. Since 3 and 4 both divided into it and divides 300, that means 12 will divide into this, for your information, 25 times. And again, since 3 divided into it and 5, so does 15. And since we're looking for a total of 18 divisors, do we have 18? 2, 4, 6, 8, 10, 12, 14, 16, 18. There's all 18 divisors. So I can take 300 and divide them by any of those numbers, and it'll go in evenly. All right, so that's the main idea with primes and composites. And I did include in the module, mainly for the next section, but you may want to look at it. I did include something with colored rods because they can also show you how to do some multiplication. And we'll look at that next time. See you next time.